So Tony, that means when you're sharing that desktop, anything you do on that screen is recorded by the implementation or not. So yeah. What do you how do you yeah. Save it. Yeah. Well, I don't know. Yeah. Driving the camera takes So apparently version of gas has not recommended. Speed went up. Yeah. She got like one no, my friend Can you send us that? What? No, I haven't. I'm here physically for this. I'm not sure. Yeah. And I installed it on. Yeah. No, I mean, Yeah.
It's got to be. My map, I mean, it's the same, back here is the same. It's just, I think you guys have the newer version of the operating system. I didn't update to the newest one. I usually I'll buy a computer and I'll leave it in the operating system until I throw it away because, sometimes that doesn't work anymore. And, the last thing you want to do is, do an upgrade that turns your computer into a brick. Okay, so yesterday I was to go through and obtain a company geometry for various molecules, and then small molecules, and then few different people doing different functionals and different geometries were benzene diamond. The first one was just be able to see the periodic trends in bond distances, bond angles, and then for both oxygen series and nitrogen series. And then the other is to look at the functional dependence of structures for benzene ions. The first one, did everybody get a structure for your small? Yeah. In the dog file, if you scroll down to the bottom, it will give you the bond distances, bond angles. So. Who had ammonia? Ellery. What is the bond distance from the bonding? Bond distance, I got 1.00166. And the angle was 106.5. How about the so back up. It's not the bottom, just a different bottom. So just put that down with bottom. Stuff right there. Okay. This is the matrix. Geometry should be just a little bit. It looks like distance matrix there. So where did you find the angle?
It's under like a table a little up in the bottom. It says optimized parameters. Then it's also like gas to be like required.
So if you do slash op, capital op. Yeah.
You go ahead and this would be there. Selected it. Yeah. You just click on that.
Okay. Sorry, the distance is
Editor,
there.
you just click on it.
Okay.
You go back to
So the distance,
you add
Yeah. So the distance is, the distance, 1.4, okay, and then the angle, 95.7, okay? What are they?
Mine was 1.525. And the bond angle was 92.1.
Okay. Water. I don't have my cheat sheet. Who did water?
No, I don't think you had water.
No, I didn't go.
Oh, you did.
0.9618. The angle of 103.8182.
Okay. Sulfur.
The bond is 1.379.
The
The
angle,
angle is 94.06. 06.
selenium.
So I got the bond length is 1.485. And the angle is 91.976.
There's a quarter.
91.17.
976.
And that's another like 97. Or 92. Okay, so we see the, the, if you will, the expected trends as you go from, as you go from left to right in the periodic table. The atom is smaller, the bond distances get shorter as we go down the column. The bond distances get longer. The biggest difference, is between first row and second row. Second row and third row is smaller. If we look at the next row, we see that the difference, again, drops off. It doesn't drop as much. The first row is sort of the big one in terms of the change of bond distance. The angle, 106, experiments like around 107, so pretty close. Goes from 106 to 95 to 92 as you go down the periodic table. For water, 104, 95, 92 as you go down. And so if we just think about the oxygen case, as we lengthen the bond, the angle decreases. Okay. Now, if you look at freshman chemistry text, or go get the classic review article on VSEPR, they talk in there about sort of what's going on with these systems, or what's going on with why particular molecules adopt particular shapes. And they talk in there about it being due to polyprinciple induced repulsion, not electrostatic repulsion. Okay. When we tend in general chemistry, we start off and we say that electrons negatively charged objects, they repel each other, and then we use that. Sometimes people use that in an explanation for why we see these sorts of structural distortions, but it's not really the electrostatic picture of the electron that's the source of this issue. It's the polyprinciple attribute of the electrons that give rise to this repulsion that you see in these CPR. And so if we think of a tetrahedral object, think of a tetrahedral object where we could have, like, say, for water, we have these two lone pairs. We have two hydrogens. And we think about the distortion from being tetrahedral, where you start off and you say, okay, the ideal is tetrahedral, right? And with the ideal being tetrahedral, the lone pairs are bigger than the hydrogens, than the bonds, and that pushes this back. Okay, that causes us to go back from tetrahedral. And that's what, and that pushing back is due to this Pauli principle induced repulsion between the electrons. So today, one of the things we want to talk about is sort of the impact of spin. In fact, electrons have spin, and impact of spin, and the big place that electrons have spin has an impact is really this sort of thinking about Pauli principle induced orthogonality effects. And before we get into that, we're going to do a little computational experiment. And what we're going to do is we're going to take water, okay? And instead of using this bond distance for water, we're going to use this bond distance for water. And we're going to optimize the geometry for water with this long bond distance. What should happen if, according to BSEPR? Let's come back to this picture here, and if we make these longer, if we said that the repulsions, the repulsion between this and this is the largest, this is next, and this is smallest. Okay. If we lengthen the bond distance, then the repulsions are going to be decreased. The electrons are further away from each other. The repulsion is going to be decreased. And so what should happen to the geometry?
The angle gets bigger because they're being pushed away less.
And so the ideal, right, according to BSEPR, the ideal is tetrahedral. Okay. I'm not dismissing what you said, because in fact it's what happens, because it is what happens. Okay. But according to BSEPR, as you lengthen the bond distance, it should approach the idealized geometry because you decrease the repulsions. And in fact, that is a true statement, okay, that it does approach the idealized geometry, just that the idealized geometry really isn't tetrahedral. Okay. The idealized geometry is to use two p orbitals, because oxygen has two p orbitals, right? And so you stretch it. And so what we're going to do, the terminal. Desktop 2 is the yeah. Okay, ooh, I can no,
But it's on the screen.
It's not there at all.
it's wanting to be instantly projected back.
Okay, let's go to the terminal. You have to open it.
Yeah. See this sort of touch screen.
Did you do this yesterday?
Did I do?
Because someone can log into your account. You recorded that.
Oh, goodness. That's probably worse than talking bad about Gaussian.
You might have to,
I don't think you did it yesterday. You didn't use this at all, but
you didn't log into the cluster history.
I don't think so.
No, I
I don't think
might
it's-
not have had.
It never screen projected, like the big
Oh,
recording
oh,
of
yeah.
yesterday wasn't screen projected. So.
Yeah.
So what we're going to do, 962. So what we're going to do is we're going to run Gaussian. So far, in Gaussian, what we've done is input Cartesian coordinates. But there's another thing, shall we say, more classic way of inputting a structure called the Z-matrix approach. When you build, like so you can build benzene by using trigonometry. Well, you can build water, or you can build anything using trigonometry in terms of bond distances, bond angles, torsion angles. You can construct a molecule. Back in the 70s, optimization of geometry was actually done using these coordinates. In fact, initially, you would just manually move the distance, manually adjust the angle to find an optimized structure. That was turned into computer programs doing that. This was back before you had derivatives. In the one-prime structure, you just had an energy, and so you just use your energy and numerically move it around. Z-matrix was convenient to do that in terms of distances and angles. Here, we want to use that facility to set the distance and let the angle optimize. And so we have here the geometry of the molecule, oxygen, hydrogen bonded to oxygen with the distance of R1. Second hydrogen bonded to oxygen with the same distance, so we're going to retain symmetry. And then there's bond angle A to H1. So the angle is our 104 tetrahedral, and then the bond distance is what we're going to set it here. And by having these separate, this first one is variables that will be optimized. If we got rid of that blank line, we would optimize both the distance and the angle. But we separated it, it's already frozen the distance. We're going to optimize the angle, see that it comes back to where it was. Then we're going to adjust the distance and re-optimize it and see what the angle turns out to be with the adjusted distance. water. This. So if we set that distance and let the angle optimize, we end up with an angle of 103.8, which is what we found before with the same basis set and the same functional. So that all worked out fine. So for sulfur, 1.38 is the bond distance. So we're just gonna, so the initial geometry is going to get set with that longer bond distance, and then the angle will be optimized. We're starting with a guess angle of 104.5. We're going to let that we'll go ahead and let that run, and then look at the geometry that we get out. So if the CPR model of a tetrahedral geometry for four bonds or four pairs of electrons, if that model were correct, as we lengthen it, it should open up to tetrahedral as we have reduced those non-bonded repulsions. It should go towards the idealized. Go to the idealized geometry, whereas in fact, it drops down to 93 degrees. It drops down to basically very close to the angle that sulfur has. And if we were to increase it further, it would drop down. And so what it's doing is it's approaching 90 degrees as we increase the bond distance in S. You said it would. It's decreasing as we increase the distance. As we increase the distance, it is going towards bonding to just two p orbitals, which is what you would expect if you thought about oxygen atom as where we have two similarly occupied p orbitals and a doubly occupied p orbital and doubly occupied s orbital, which we're not going to show. Take the atom, we bring up another electron to make the bonds. We put them in a singlet pair. Okay, and think about what's going on between those pairs of electrons. The okay, so day two. Well, okay, day two. What we're going to think about is what the role of spin is in molecular species, and then we're going to look at the spin direction and so forth. But Pauli principle, electron spin, and the Pauli principle, wave functions of electrons have to be antisymmetric. The interchange of coordinates of the electrons, the wave function has to change sign. So if we were to write 3 different orbitals, electron in each of them, and then think about exchanging the coordinates of electrons 2 and 3. So electron 3 was in orbital B, or was in orbital C, now it's in orbital B. We just permuted those. And the Pauli principle says if you do that, this wave function must be the negative of the previous wave function. That ultimately ends up with a determinate picture. But what we're going to think about right now with that is if we start with, for example, a wave function here, and think about permuting the coordinates of electrons 1 and 2. If we start here, we permute it A and B, and we can say that this permutation operator needs to make the wave function change sign. If we started with this as our initial wave function, where we have changed the sign of the second one, if we permute that, then the first one flips, the second one flips, and this is minus that. And so that permutation operator gives us our anti-symmetry if we have all the products of permutations. What if A and B are the same? Well, if A and B are the same, we do the permutation and we get 0. And so what that says is something that we talk about in freshman chemistry, is that you can't put 2 electrons in the same orbital with the same spin. This is just in general, if we're thinking about spin orbitals, we have a spatial part and a spin part. And 2 electrons can't be placed in the same spin orbital. What if the spin orbitals are not the same, but they overlap? Well, if we start off with A and B where they're orthogonal, we construct a new one that is a linear combination of them so that it won't be orthogonal. And then we end up with the overlap between these is lambda. If we consider this permutation for this new case expanded out, what you end up seeing is that this part here goes away, and we're back to our original A and B. And so if we let the orbitals overlap, which you can do, okay? If you let the orbitals overlap, the anti-symmetrizer or permutation operator removes that overlap. It's projected out, so it's not an approximation to take spin orbitals as being orthogonal, or it's not an approximation to think about these pairs of electrons as being orthogonal. And so in this picture, where is the overlap, or where is the overlap coming from, or is in our picture that gets distorted? Well, if we start thinking about this one, in this bond pair, okay, you say, wait a minute, electrons are in the same orbital of opposite spin. Okay, and so the spin orthogonality lets you put 2 electrons in the same bonding orbital. So this is fine, that's fine in terms of a bond. This orbital, the hydrogen, and this p orbital, at 90 degrees, they're already orthogonal, because this p orbital has a plus and a minus phase. This is symmetric, that's 0. This electron and this p orbital are already orthogonal at 90 degrees, okay? And this p orbital and this p orbital are orthogonal at 90 degrees. So the only thing that's left to think about is a hydrogen with the hydrogen, okay? Those 2 are not intrinsically orthogonal to each other. Those 2, they're in space. It's not a bonding distance, but it's fairly close. And so these 2 are not orthogonal. The Pauli principle, the anti-symmetrizer, says it's not an approximation to take them as orthogonal. okay? And so for these to become orthogonal, what can happen is, what can happen is if we bend the angle, they get further away from each other. And the overlap between them has a profound distance dependence, an exponential dependence on distance. And so opening up the angle from 90 to 104 degrees decreases the overlap. They get further apart. You go to sulfur, where the bond distance is intrinsically longer, you have the same orbitals involved, but it doesn't have to open up nearly as much because you're further out on the overlap curve for the sulfur case. Or if we just stretch the distance in water, we're further out and the overlap has decreased dramatically. So the equilibrium angle really ought to be, for these cases, it really ought to be 90 degrees. It shouldn't be a tetrahedral angle. That's not the sort of proper reference point. And the effect is due to this Pauli principle induced orthogonality that comes from, or that is due to spin in the system. Does that make sense? Any questions? Yeah.
So I know it's decreasing, like the big difference is between the oxygen and sulfur, but like the next one is not that big of a difference, but like we could assume that the next atom is like even closer, being like planar because of the need to,
Or 90 degrees. Yeah.
Yeah, so that'd be like 90 degrees all in like one plane, just because it's like this that far.
Yeah. In terms of where the bonds are. And so for water, for pH3, or RCH3, you got 3 p orbitals that are singly occupied. And so they're all 90 degrees with respect to each other. And it gets umbrellaed out for ammonia because of the shorter bond distance in ammonia. Okay. So the next thing we want to talk about connects in with the benzene dimer work that people did. How did that work out? Did everybody get a structure?
So one didn't turn into the structure that I was hoping it would, or
Uh-huh.
hoping to. I was supposed to get the two that are parallel to each other, and it optimized itself into the T shape. So I tried it again, and it made one that was parallel to each other, but then bonded the two structures together.
Yeah, that was probably close enough that it carried out a chemical reaction. But yeah, how did yours work?
Mine did sort of the same thing when I ran it. It didn't quite get into the T shape, but it's definitely small.
Okay, so which functional did you have?
I had the ATFD, or AFBD, I forget which one it is. The one that starts with an A.
Okay, how about you?
I had the one.
And so it distorted. Who had B3 lip? Did it
I
work?
read it, but I wasn't able to look at it using calcium.
Okay, because we're having issues with calcium. How about the T-shape folks?
Yeah, I was able to do that, like I had it without that calcium.
It just stayed as a T-shape. Okay, what was supposed to happen, which didn't happen apparently, was that the B3 lip and PBE1, PBE, which all three of these functionals are hybrid functionals. They have this exact exchange built into them. But the difference between them, other than everything is different between them, the difference between them that we were interested in was in the APFD functional, there's that D at the end. of it. And not working.
What?
No, okay.
I just got missed it all.
Okay, let me find a picture. I want to show you, so the APFD functional. No, I can't find it. The APFD functional, that D stands for dispersion. And what they did was, if you took something, say like benzene dimer, and you looked at it as a function of distance with different functionals, you compare that to a more exact result. What you find is that they're sort of waffling as a function of distance, sometimes above exact, some functions below exact, and they combined a couple of functionals together to wipe out the long range part. And by doing that, that allowed them to add in. So if you have a curve that is perfectly repulsive, that allowed them to add in a 1 over R⁶ dispersion term and get a reasonable binding energy. And if you look at in the APFD paper, they have plots of like benzene dimer and lines, all that sort of stuff. All of the other functionals, you can get sort of weirdness because you have like artificial wells in different places. You could actually find 3 or 4 minimum as a function of distance, which is very physical. But I haven't messed around that much with benzene dimer with APFD to see the difference. So we have the T shape where we classify where we have the parallel displaced. See, I'm not an organic chemist, I can't draw these really beautiful rings. But we have a parallel displaced structure and a T shape. For this one, dispersion dominates the interaction. For this conformation, electrostatics dominates the interaction. And so as a function, if you don't have dispersion, you really can't get this. It doesn't stick. And it should, it's depending on your starting structure, sometimes it'll just dissociate it essentially infinitely apart, which takes a while, but it's kind of scary. Whereas this one can stick with almost any electronic structure method. And so as a function of adding dispersion in, this structure starts coming down and becomes competitive with this structure in terms of binding energy. But it is a function of level of inclusion of electron correlation. And so I want to talk just a little bit about, okay, what is electron correlation? Okay, so if you thought about just H2, you thought about putting 2 electrons in one orbital, which has a functional function on the right, and consider the electron amplitude or probability. Electron 1 is symmetrically disposed over both centers. Electron 2 is symmetrically disposed over both centers. And so in fact, you have like a 50% probability of the electrons being in exactly the same place. And electrons being, and in terms of, say, wait. didn't we just say you can't have two electrons in the same place because they have similar? These electrons have opposite spin. And so they're intrinsically orthogonal to each other, but there's still electrostatic repulsion between them. They don't want to be at the same place. So how about wave function? And that is where we put one electron on the left and one electron on the right, and combine it with the flipped case where we have the electron that was on, the first electron that was on the left now is on the right, and vice versa. Either the plus or the minus combination of those two. And in that case, when electron 1 is on the left, electron 2 is on the right, and when electron 1 is on the right, electron 2 is on the left. And so the positions of the electrons are perfectly correlated. They stay away from each other electrostatically. And what we would say, because of that, is those that we've included electron correlation. The positions are correlated or connected to each other. For that case. And so this the bottom one is a triplet case where we get at that by putting one electron in G and one electron in U. And so for triplet coupling or high spin coupling, the motions are correlated. For a case where we have them singlet coupled valence bond description, they're also correlated positions or motions of the electrons that are correlated with each other. And that correlation allows the electrons to be away from each other and lowers the energy of the system. Okay, we can take and make the minus combination where we take our first wave function, product wave function, and add on a second product wave function. First one where you put electrons in the G orbital, second where you put both electrons in the U orbital. We can take that, expand it out, okay, and we end up with a wave function that is a plus combination. And so by adding these together, or subtracting them from each other, we've included electron correlation. Adding this second configuration where we've taken the electrons out of the G orbital and put it into the U orbital is called an excitation. Exciting the electrons and adding in electronic excited states into your ground state picture allows you to include electron correlation. And there are a bunch of different ways that one can go about doing that. But what we're interested in here is the case where we had triplet H2. We said that those electron motions were perfectly correlated, but not completely. Okay, there are other attributes, and we started thinking about triplet H2, where we have one electron, if you will, on the left, one electron on the right. We have that triplet case. And we consider, again, an excitation where we take these two electrons and excite them into a 2p orbital. Instead of into the antibonding case, we put it into a 2p orbital. We expand that out. And what we see is the coupling matrix elements between these two goes as 1 over r to the 6th, or excuse me, 1 over r to the cubed matrix element squared. So that goes as 1 over r to the 6th. Okay? That type of electron correlation, you can't really put into a picture, but we call it dynamic electron correlation, and it's dispersion. And so dispersion is a correlation between electrons of the same spin. If you go through and look at any of the correlation functionals in the literature, they're all based on the density and the gradient of the density. You can't really put this into you can't put this into a density picture. And so density function, and normally, as we said earlier, that triplet state was perfectly correlated. You can ignore the correlation. And so for 30 years in density functional theory, it's like, okay, we don't need any same spin correlation. It's not important. It doesn't exist. Well, turns out that same spin correlation is dispersion. And you know, dispersion is actually always there. Dispersion makes benzene dimers. I mean, that's why we have liquids, right? When you do these simulations, you always have a 612 potential. You always have that dispersion there. And so people have started adding on to the density functional dispersion term to account for this intermolecular nature, intermolecular electron correlation, which no one has figured out yet how to truly include it into the density functional. Okay, so thankfully we still have an hour to go. The other thing we want to talk about was transition states. Okay, and if you look at this picture up here, where what we're interested in doing is finding that point on this hyperbolic paraboloid surface where it comes up and we go over and down the other side. The other dimensions are normal sort of paraboloid shapes, but we want to find that point. And if you thought about minimization of geometry, what you do is you find the first derivative and go against the derivative as you march downhill to a minimum. Here, we don't want to march downhill to a minimum. We want to march downhill to a minimum in n-1 dimensions, and in that last dimension, we want to go uphill. To be able to do that, you need second derivative information to be able to march uphill. And if you just take a normal Newton-Raphson procedure and allow for there being a negative eigenvalue, that which is your reaction coordinate, you can march uphill from the minimum up to a saddle point. And we'll go through basically how you do that in Gaussian, and part of your homework is to calculate a transition state. Okay, so if we're thinking about unpaired electrons, we want to look at it, and if we thought about our product wave function where we have a certain number of electrons in alpha spin orbitals, again, product wave function, and a certain number of electrons in beta spin orbitals. The alpha spins have to be orthogonal to each other, or we can take them as being orthogonal to each other. The beta spins, we can take them as being orthogonal to each other, but the alpha spatial orbitals and the beta spatial orbitals don't have to be orthogonal. They can overlap. Okay, that overlap, if it comes into play, is called polarization, okay? And it lowers the energy of the system and can play a role. But if we want to look at this, we look at these orbitals, which are not orthogonal to these orbitals. They can be mixed up. If you just look at the alpha orbitals and you look at the beta orbitals, it's like, okay, they don't line up necessarily. They're hard to really see in terms of whether they're the same orbitals or not. And so what we tend to do is instead look at densities. And so the alpha spin density is basically summing up the product for alpha orbitals. The beta spin density is the same thing for the beta. And what we're going to look at is the difference between those two. We're going to look at the net difference between alpha spin and beta spin density. That net difference that we get out of that is actually an observable. Okay? It's actually, if you do an ESR experiment, the coupling between the nucleus and the electron is that spin density, a portion of that spin density. So it is an observable. In addition to being able to see by X-ray crystallography absolute electron densities, we can look at spin densities by ESR spectroscopy. Computationally, we can look at spin densities by in Gauss view. One of the options that is to, instead of plotting like the total density, you can plot the net spin density where it goes through and does the summations and subtractions. And I did a calculation on benzene cation. So I removed one electron from benzene, and so the number of alpha and betas now are different. So the convention in Gauss view is that alpha spin density is shown as blue, beta spin density is shown as green. Okay, and so you can have a system where you have some alpha spin density, some beta spin density, and so you can see the sort of nuances. In this particular case, for benzene, it's I use the optimized symmetric geometry, and so there's no real need or mechanism for it to spin polarized. And so we end up with this picture where we have unpaired electron density on the ends more than the middle, okay, in that system. And so this isn't, we look at a molecular orbital, which we can do. Going to generate some of the molecular orbitals of benzene, and this is the highest occupied molecular orbital of benzene. Benzene, the pi system, because it has D6A symmetry, you have an A and an E set, so two degenerate E orbitals and an A orbital for the occupied pi system. And this orbital, perhaps not surprisingly, looks similar to the spin density. Not exactly the same, okay, but similar to the highest occupied molecular orbital. The next one. This molecular orbital is the same energy as the first one orbital we saw. It is the second member of that E set that forms the pi system of benzene. Okay. Tomorrow, when you start talking about excited states, you're going to do a calculation that looks at adding electron correlation involving these pi orbitals and looking at excited states. The next one down, so we had 21, 20, those are pi. We look at 19. We look at orbital 19, it's not pi. Orbital 19 is in the sigma system of benzene. We look at 18, It's also made a combination of CH and CC sigma bonds. And finally, if we look at orbital 17, that's the symmetric pi orbital, the A1 pi orbital of benzene. And so when you do the CAS calculation tomorrow, you want to look at the pi electrons, and so you're going to have to mess around to get that electron, that orbital, to be where it needs to be in your pi system, pi space. Okay, so put that for now. So we can look at radicals when you are, in your assignment, you're going to have a radical to look at. By looking at the spin density, you can see where the unpaired electron is inside or unpaired electron or electrons is inside the molecule by plotting the spin density for it. You guys are probably young enough that you've never had to live through watching home movies or having to look at slideshows where people go on a trip and they bring back all the slideshow and they're really excited about it, but you're kind of bored after about 10 minutes. That's what you're going to be experiencing, okay? So I'm going to show you some spin densities where it's just really exciting to me, okay? And if you fall asleep, just make sure you keep your eyes open, all right? So I don't know if you're asleep. No, I don't actually have it there. Oh, worry about that later. Okay, so what we're going to look at is a molecule called chromium ACAT, or chromium tris acetylacetate. In some schools these days still have it where in Gen Chem lab you actually make this molecule. It's really brightly colored and really air stable and easy to work with, but it's not an organic molecule. It's a molecule that has a transition metal in it. In this case, the molecule is a chromium, and so chromium ACAT. It isn't exactly octahedral, but it's nearly octahedral in geometry, in inorganic chemistry. We think about where the d orbitals are, the d electrons in the system, and this symmetry, which is octahedral, ends up taking your 5 degenerate d orbitals and splitting them out, where there are 3 down and 2 up, and figuring out where the electrons in there and different metals and different ligands. Inorganic chemists have been doing since the 50s. And still actually actively focusing in on where these electrons are. For chromium, the acetyl, so chromium out here in the middle, group 6 valence electrons. Each of the acetylacetonates takes off 1 electron, and so we're left with 3 valence electrons on chromium. They fill this lower set by having 1 electron in each of what's called the T2G orbital, and if I had already generated the spin density for that plot, we could look at it, but this is symmetric. Each one of these orbitals is this cloverleaf shape of a d orbital, and you stick 3 of those into 3 different orthogonal directions, and you get this wonderful little cube of spin density that looks just like a little cube buried right in the middle of this. I didn't transfer the file over to be able to look at that, but we can look at that later. But this is chromium acetyl acetate, and what we have there is, if we take this and think about the lowest energy excited state of the system, we might think that what's going to happen is you put an electron up there. Okay? No. I mean, it does that, but that's not the lowest energy excited state. The lowest energy excited state for chromium is where you just do a spin flip. So we have 2 alpha electrons and a beta electron. They're all still in different orbitals. And in this picture, you rotate that around, you can imagine if that green were blue, it would be a cube. Okay, but it's green. It's the opposite spin. And so we have 2 alpha spin electrons and 1 unpaired beta spin electron in that excited state of chromium. Okay. There's another representation for this. Where instead of having the 3 electrons in different orbitals, you have the electrons 2 in 1. Okay. Those 2 configurations are actually degenerate in energy, and they make a doublet E state. But this, the first time I saw that, I was like, wow, that's really neat. That it actually does. You can see that spin flip. It is simple. Now, next thing we want to do for this in terms of thinking about spin densities. So this was chromium 3. Okay, you take 3 electrons off. What happens when we add 1 electron to that? Well, you say it's a chromium 2 complex, right? You add 1 electron to that, it's a chromium 2 complex. And we could put the electron here, or we could put the electron here. We could put it here, or we could put it here. And by looking at that excited state, we can figure out where that extra electron, or by adding the electron, we can see where it ends up in the complex. And so, again, we can use the spin density plot to tell us where the extra electron goes to. So this is this chromium 2 ACAC. If we look at it, we got that cube in the middle. So we have 3 unpaired electrons on the chromium. And the extra electron to the chromium 2 actually doesn't go on chromium. Yes?
Or are you choosing a specific value for density?
What would that, wait,
Yeah.
It doesn't, I mean, their default is smaller. This one is it's more, you can see things better. for that contour. The other one, things tend to be smeared out, and so I like the 0.003 as a, it is more compact, but it shows the character. It doesn't really, the character doesn't really change, it's just harder to see it at the other contour. That contour was developed or set based on organic molecules as opposed to transitional containing ones. And this one is for transitional, it's a better sort of picture. So the extra electron went on the ligand. Okay, the extra electron went on, so we have spin density, alanine, the acetyl acetates, all of that. Extra electron went on the ligand of opposite sign. Okay, so if we added in, so if we take this and add in, I'll just call it pi star, add in the ligand orbital, the extra electron went out onto the ligand of opposite spin. So if you rotate that around, we see that the extra electron is in a set of p orbitals. It is in a pi orbital on the acetyl acetate, but it's symmetrically disposed over all three, but of opposite sign. It's anti-ferromagnetically coupled. Yes?
If we were going to say that we know it didn't go to chromium because it would have to be green, it'd have to show up green, and there's no green in the cube.
Well, if it's stuck on chromium, it would, instead of having a cube shape,
Yeah.
it would be not a cube shape.
Mm-hmm.
It would either have some green or just reduced blue, not symmetric blue.
Mm-hmm.
It would be different. And we can actually also take this, we got this spin density matrix, and we could diagonalize it and get orbitals, spin natural orbitals out, and look at those as well. But but so it did, and you know, oh gosh, I guess 5 or 6 years ago, first time we saw this, it's like, you gotta be kidding. You know, because of chromium 2, that's not chromium 2. I mean, right? That's still chromium 3. But in terms of the magnetism, there are 2 unpaired electrons. Okay, because this is coming in of opposite spin. So these are, if you will, spin paired, 1 left with 2. So in terms of magnetic interactions, 2 unpaired electrons, you think chromium 2. In terms of where things really are, they're actually 4 unpaired electrons. They're just unpaired magnets. And we can look at the spin densities to see that sort of effect. It turns out that it actually has significant impact on chemistry. Instead of having the unpaired electron on the chromium buried in the middle, unpaired electrons on the outside, it's more accessible to chemistry. So it actually has practical ramifications on what's going on. Yes?
Down at the bottom there, it says neutral doublet. Is
Yes.
it something neutral? It's just a doublet. We got another electron. So it's just like, because it's chromium 2, so it's still.
And that's, I mean, that's wrong. This label is not correct.
Okay.
It's just like not enough information in that checkpoint file. And so this was actually, it's an anion. We added extra electron, and it's not a doublet. It's a triplet. And so this is just, it's not that it would be nice if it were correct. But, yeah. Okay, so enough of an adventure in spin, unless you want to see some more. I got these like doing. But okay, so what we want to do for the last part of what I'm covering is when we want to think about transition states, calculating transition states. You know, chemistry by and large is change, right? Chemistry, we tend not to just look at static structures. We tend to think about doing something talking about doing chemistry. So an important part of understanding how chemistry happens is understanding what happens along the reaction coordinate. And the most straightforward point to, if you're going to think about a point, the most straightforward point to think about for a reaction is the transition state or saddle point for the reaction. And we can calculate those sorts of things. There are a number of different ways to go about finding the saddle point, and what we're going to calculate is the transition state or saddle point for the reaction of methyl radical with methane. The barrier for that reaction is just a few kcal mole. It's a small barrier. If we thought about taking two methanes and reacting them to make, say, H2 and ethane, really large barrier. This has a small barrier. It occurs readily in the gas phase. And what we want to look at is, okay, what is the transition state for that? What does that look like? And so one thing you can think about doing for finding the transition state is to start off with the reactants. And you know how we did that constraint? We fixed the bond distances and optimized the rest of the coordinate, the angle. Here, you could start off and say, okay, I'm going to systematically march along forming this bond. I'm going to go up in energy, up in energy, up in energy, and then I'm going to start going down in energy. Okay, so we would move, if we had a constraint, we'd go along, and then come down on the other side and say that that is the transition state. You can get at that same sort of thing in condensed state systems by doing umbrella sampling or other techniques. Here, you could fix that, move, find this point, and then call that the transition state. That works out okay sometimes, but if you have a couple degrees of freedom, not so good. And so what we're going to do, rather than doing that, is we're going to have a guess for this geometry, and then we're going to use the second derivative and Newton-Raphson optimization and find the saddle point through a straightforward minimization. That means we got to have a good guess, because if you think about that surface, think about that in terms of sort of parabolas. Over here, you're on the reactant parabolic surface. You're on the product parabolic surface. Here, you got an inverted parabola. That's okay. At some point along the way, you cross from having a positive second derivative to having a negative second derivative. If you're in this region, you can slide down here instead of going back up there. That's a problem. And so what you say is that you need to be within the radius of convergence of the saddle point for it to be able to lock in. And part of what you're going to be doing for your calculations is finding out how to get it within that radius of convergence of this saddle point, so you can march uphill to the saddle point. Okay. So and we know the methyl radical is flat right? But along the course of the reaction, it starts becoming more pyramidal, and so having a pyramidal starting guess is reasonable. We could bring it in, and for our initial guess, we know that the initial bond distance, 1.07, 1.09. In the product, it's infinite. Well, we're not going to average between infinite and 1.07. And so we're going to say, okay, this is partially broken. What's a good partially broken value? How about 1.4? Does that sound like a good value? Because it's not broken, 1.5 would be almost broken, but 1.4. And actually, I don't remember what the number should be, so we're just guessing 1.4. And we're going to end up finding out, okay, are we within the radius of convergence? If we go to a South point converter, if we didn't, we aren't, and we're rolling back over here. If that was too long, we might try 1.3. Try to guess. Now, you say, gee, this guessing, wouldn't it be easier just to do it the systematic way? Well, sometimes yes. Usually the first time you start on a new sort of system, you do a systematic march, but then you sort of know what to do next, and so you don't repeat that arduous process. Okay, so we can set that distance. So by turning on the distance tool in Gauss view, we can set distances, and we don't want to let this one move because we already just set that to 1.4, and so we're going to fix that in, and the other end, we're going to bring that in because here we're taking methane plus methyl radical, it should be degenerate. The reactant, the product, the same energies, and so the transition state should be halfway in between. Some of you are going to have cases where it's exothermic or endothermic, so it won't be completely symmetric. Want to tweak things a little bit. Okay, one more thing is adjusted to being collinear approach. Why? Because I know that's what it wants to be. And one more adjustment, just is Noah wants to be sort of a staggered orientation, keeping those bonds, those sort of spectator bonds, as far away from each other as possible. Okay, so we sort of tweaked around, guessed the geometry for the transition state, and now what we're going to do is set that up.
So which value did you not fix? Which value?
I actually haven't fixed anything.
Okay.
I've just adjusted things to get the geometry to look reasonable.
Oh, okay.
So I haven't constrained
preliminary.
Yeah, so I haven't constrained, and hopefully we won't end up needing to constrain anything. Yes.
So all the stuff when you get it fixed, it was only just for the moving of it. It's not actually for the
Yeah.
doing a calculation.
Yeah. But as the starting guess geometry, the initial starting guess, and we're not going to. Now, if this fails enough, for fitting a molecule, what you can do is you can do some constraints, and let everything else relax, and then let it go free. But again, just like things like basis sets and functionals, it's an art. Over time you figure out, okay, how do I get to the answer in a time efficient way. Okay, we're going to do a opt. We're not going to optimize to a minimum. We're going to optimize to a transition state. We're going to calculate the second derivatives always, because without second derivative information, there's no way to know how to get to that point that you're going to just tend to roll down to the ground state. You can sometimes accidentally go through a first derivative optimization. You can march, because the derivative is going to zero, you can march into a sound point when you don't want to, but by and large, you need that second derivative information to really help you out. Okay, I think that's their method. With ground state wave function, density functional theory. We're going to go to our more usual basis set. D functions on the carbons, P functions on the hydrogen, because that hydrogen in the middle is really involved in the chemistry. Is there anything else? I think that's it. And so we just sent that off to calculate the transition state. It'll run a little while where, yes. So before, if you were to go through the Gaussian input, what you see is you start up, you do a self-consistent field calculation, then evaluate the derivatives, make a geometric step, reevaluate the energy, make a geometric step, and march downhill. Now they have extra bells and whistles to help that happen quickly, but that's the basic procedure here. Wave function, first derivative, second derivative calculation, make a step, and go down and proceed. And along that way, we'll see that there needs to be, and it hasn't complained yet, there needs to be at least one negative eigenvalue for this inverted region. We have to have one negative eigenvalue or imaginary frequency by default. The program, if you don't have that, it stops and says, no, you're not doing the transition state, you don't have a negative eigenvalue, or you have two. What do I do? And if you run into that circumstance, we can work on making that happen. Yes?
You form the radical on Gaussian, or does that happen in the
But by having, if you will, there's 6 electrons on each carbon, 4 more, 3 more. We have an odd number of electrons, unless we made it an anion, and then it would be closed shell. But we just sort of didn't do anything, and so it's a radical. Yeah. If we add electron, then we could do a carbanion extracting a proton sort of reaction. But we're just looking at the radical case. Yeah.
How do in setting up a calculation, how do you get the spin occupancy? Like, how do you tell it to calculate that?
Tell
The spin density?
On like the cluster, there's this like AMO, and then there's also a thing called spin. And again, not very original, but that generates a spin density cube file. Okay, so the wonderful thing, and it's, running these things inside Gaussian is really great because for these small molecules, it goes through so fast that you can really know it. Because you want to look at it, it's moved. But this, so this maximum force, displacement, changing coordinates, change in coordinates. Yeah, I will be able to get there. I will. I swear I'll get there. Need to use a bigger basis set, so it'll be slower. I have to wait. Okay, I was trying to, in the middle, in each step, it gives you the, it diagonalizes that Hessian and it gives you the normal directions, and you see that there is one negative eigenvalue, or it should be able to see that there's one negative eigenvalue. Yay! I saw it quickly. You see? Right up above here. You see that? Come on, finish. This isn't that hard. It should have been done. I mean, it does have one negative eigenvalue. It should have been done before this. It wasn't that bad of a guess. While that is doing its thing. So, for your homework for today, first thing is I want you to calculate a radical and look for the density plot for a radical species. And then the second thing is to optimize the sound transition state, find the sound point for different small molecule reactions. And if this methane plus methyl radical finishes, we should have a fairly good guess for what that CH distance is. If you substitute in nitrogen, okay, for if you saw here, this one was OH is 0.96, and NH equilibrium is 1.01, and a CH is around 1.09. And so the others, you can scale down your starting guess distance sort of accordingly. Some of these, oh shoot. I'll change this. This isn't supposed to be this molecule. I'll put it back up. But this is supposed to have an extra oxygen on it. And where's the extra electron in nitric oxide instead of nitrous oxide? So where's the impure electron here? Basically what's going on in this case. You can look at these and see where the impure electron is. And allo radical, it'll end up being symmetric. And we can see that. And then ozone, say, ozone is not radical. Well, it turns out that it actually is. It has radical reactivity behavior. And so that one will be a little more interesting to get it to be a radical system. But it does radical extraction chemistry as well as other kinds of things. Yes?
From on there, that's resonating.
Yeah.
If I put it in the Gauss view, does it matter which one I do?
No.
Okay, that's what I thought.
I mean, and then in fact, yeah, you can start if you wanted to with a regular CC double bond of like 1.3 and this is 1.5. It'll march it into being symmetric.
Okay.
Yeah. the challenge with all of these cases is that, Gauss-Q is set up for organic molecules, and it likes everything to be bonded. And so you gotta you will build the more conventional structure and then eliminate one of the atoms, one of the hydrogens, to make the radical type structure. Just like with ChemDraw, you try to draw a radical, it keeps adding hydrogen back in. It's like it's trying to tell you this is not normal chemistry. But it will let you ultimately go ahead and do that. So when we're done here, I'll edit this file. So this is what's supposed to be here is just an extra oxygen on here, so N2O. Yay, it ran. We're going to open it. And we got this symmetric structure. We can measure things like the distance. 1.347 or 1.35. So 1.4, just a little long, but an okay guess. Close enough that it was able to march in and find the south point. The other one, and the measure, if you look in the literature for people who calculate the transition state, thing that they basically always do or always have to do is they have to report that, yes, I have one imaginary frequency. I have one negative eigenvalue. If you they didn't have a saddle point. And so here, in terms of the frequencies, we have a rather large negative. I mean, this is, really should be imaginary, but how do you write that imaginary? But the vibrational frequency minus a negative 1638. Next mode, really tiny, and then we have these other vibrations. So we didn't show vibrations yesterday, but we can show them today, and it gives you a vibration of a higher spectrum. But if we tell it to show it, so this is animating the, if you will, the classical nuclear displacements associated with that vibration. And so this negative one, I mean, it is the reaction coordinate. It is going from one side to the other side. That really small one is torsional mode, but it's through that central, transition state. So it's really, instead of being around 300 wave numbers, it's really tiny because there isn't a lot of connection between those terminal CH bonds. And you can look at all the different vibrational modes for the molecule in terms of what's going on in that case. Yes.
How come one hydrogen of each carbon isn't vibrating as much as all the other ones?
That's in terms of the in terms of these modes, for like a methyl group in particular, you have for three things, you have typically an A1, a totally symmetric, and then an E, where the E, looks sort of like a p orbital that they're referring with. So part of it and the other one. So let me just go the ones around it. See over here, these were, if you will, that this one is, and this one being left out. Same energy as this one, where the other two aren't happening so much. And so they're degenerate with respect to each other. There we have the symmetric one. But the others, and so when if your molecule has significant symmetry, you can see sort of the underlying A and E nature of these degenerate pairs. It's all stretch stuff, bending motions. I mean, it's like you can sit and stare at these things for hours, or not. Questions?
How did you get to that page where you like where on the like the Gaussian bar did you press to get to the one where it shows all the bending?
Stop this. And instead of animating, you can actually just show the displacement vectors. But okay, back to, so we're here under results. So under results, we have this surface thing, and now we have vibrations as an option. If you come to that point and you don't, if the vibrations isn't accessible and it's faded, then it didn't work. Okay, but so they should be there.
So you're opening the what file?
The checkpoint file.
Oh.
Sorry, I'm still a little confused about this spin part. I'm still a little confused about how to tell it to use frequency, or does it just automatically do it?
Where in Gauss view or in
Sure, just about anything.
all right, so in Gauss view, so we read in the checkpoint file, we have all the information about.
If you just do a normal calculation, it'll be in the checkpoint file?
Yes.
Oh, okay, that was my question.
Well, obviously sort of go to surface contours, and we're going to make a new cube. Now, because we have an unpaired electron, we have this spin density option.
Oh, okay. So
And
just by inputting a compound with an unpaired electron, it will automatically generate it.
but the wave function will automatically have a different number of alpha and beta, and then and so the orbitals are on there, like this program or the other programs, they go through and sum up and generate this alpha spin at the alpha density, the beta density, do the numerical subtraction, okay, and in terms of the display. And so here, the alpha spin, we have this radical, the alpha spin is symmetrically delocalized over, and there's a little bit of beta spin density, spin polarization on the hydrogen. Other questions? Okay, so that's it. I'll be around this afternoon if you have questions as you're going along. And for ozone, we're going to have to do a little extra, but you got to do ozone, right? You can't, it's not that ozone.
You just leave it as you make put the three oxygens together and then just delete the hydrogens. Will it understand it as a diradical at that point?
No. No, it won't. I mean, it could. That would be sweet, but no, it'll go through and you'll be able to do a regular calculation on it. It just won't be ozone in terms of the right electron structure. We have to go through and do a little extra work on that. It's amazing, right? In my freshman chemistry, you go through and you learn how to build these Lewis dot diagrams, connect everything together. And you always talk about things that are closed shell. You don't do the odd ones because that doesn't follow the normal rules. And so you just ignore all of that. Well, in this sustainability chemistry course, it's like you start looking and thinking about all of the important molecules in the atmosphere and everything. They're all radicals. It's like, whoa! It's like we exclude all of the interesting stuff because it's not so easy to do. But air pollution sorts of things, ozone, O2, ozone hole, it's all radical chemistry. And you can't do the normal sort of octet because there is no octet. But it's interesting, there's a lot of interesting stuff out there. Alrighty.
Oh, and for the state one, is that just a geometry optimization calculation?
Yeah, I mean, you're not going to be able to test a good geometry for these radical species. And so you have to do it on.
Okay. And within that, the results in that, all of the density and stuff will be there.
Yeah.
Okay.
What exactly is that 1.4 that you put in? What exactly was that again?
That was the C8 long distance.
Okay.
And so 1.35 would be a better guess.
Okay.
Than 1.4. But, 1.4, it came in. Right.
And so like if you were to use 1.5, you could end up getting problems with it.
You could.
Okay.
It might, yeah.
It
might just-
far away.
If it's too far away, it might just roll down. I mean, it's like you're trying to balance a pencil on this point. And, that's fun to do. It's easier if you have a bunch of salt around, but you can do that, but it tips off.
Okay.
And so you want to be close and get it fairly close to be able to stay there.
Okay. Thank you.
And when you're aligning it, you're trying to hold the hydrogen like close to the carbon, or depending on the structure.
Yeah.
Okay.
Yeah, and all of these should be fairly nearly collinear between the two heavy atoms and the hydrogen. It should be a nearly collinear approach. When you can think of the atoms with their lone pairs, it might bend a little bit, but a collinear starting guess is definitely the way to go.
Now with ethane, when aligning it, it's like you're trying to provide the hydrogen with trying to get it cold in. I feel like it's kind of hard to get. I was working on it beforehand. Like you're probably gonna have communication, right? When I try to get this point out, try to get I would sort of try to dock it where those two hydrogens are on top of each other. Well, no. So you just put another ethane out there, and then if you do the thing where you hold this down, and then drag it in closer. Yeah, put it out with that hydrogen right on that other hydrogen. On top? Yeah, right on top. Okay. Okay, and then if you rotate it around, now it's not quite, so we can do that same thing. Yeah. Get on top of it, and then when you have that, blow away one of them with the dilute function, which is up here, and then you just delete one of them, and then you can adjust the distances and so forth. Oh, okay. Thank you.
Here.